a cinematic, poetic evocation of time itself, the endless river, flowing only one way, carrying galaxies, civilizations, and lives toward an unknowable future. Reflection on humanity's most fundamental assumption that time always moves forward. Introduce the central question: what if this flow is not eternal? What if time itself is unstable, capable of folding, collapsing, or reversing? Philosophical tension: if time collapses, what happens to memory, cause, and existence itself? Would everything we know be erased, or endlessly repeated? This is not simply a question of physics, but of destiny, reality, and eternity. Hello, I hope you are all doing well. And welcome to the Whisper Science family. Let us step into the mystery. Time, the invisible thread that binds every heartbeat to the turning of the Earth, every orbit of the planets to the slow drift of galaxies across the night. Civilizations have risen and fallen beneath its quiet reign, yet no one has ever touched it, measured it directly, or seen its shape. Humanity has only ever lived inside of time, as fish live in water, unaware of the medium that contains them. And so, across centuries, the first attempts to explain time were less about clocks and equations, and more about stories, symbols, and myths. In the cosmologies of ancient India, time was not linear, but circular and eternal. Wheel turning through vast cycles of creation and destruction known as the yugas. Entire universes were born, flourished, dissolved, and born again, without beginning or end. To the Mayans, time too was cyclical, a sacred rhythm reflected in their intricate calendars, in which the end of one great cycle was never death, but the seed of another beginning. The Stoic philosophers of Greece imagined the ekpyrosis, a cosmic fire that consumed the universe only to let it emerge once again, reborn from its ashes. To the ancients, time was not a line but a circle. Eternity was not a horizon stretching forward into the unknown, but a wheel, forever turning. But with the rise of modern science, the wheel began to straighten into a line. In the 17th century, Isaac Newton declared that time flowed absolutely, uniformly, and independently of all things. For Newton, time was the great cosmic stage, moving forward with a steady tick, whether or not any actor was present. Seconds, minutes, hours, all passed identically in the silence of empty space, as they did on Earth. His vision of time was mechanical, eternal, a river that could never bend, halt, or change its pace. For centuries, Newton's picture reigned unquestioned. The laws of physics were written upon it, as on a perfect grid, each equation unfolding upon the steady current of universal time. Even as the Industrial Revolution invented ever more precise clocks, from pendulums to pocket watches, humanity's faith in absolute time only deepened. To be modern was to synchronize with the tick of gears, the schedule of trains, the pulse of machines. Yet in the early 20th century, a quiet revolution began, one that would forever fracture the Newtonian dream. In 1905, Albert Einstein published his special theory of relativity, revealing that time is not absolute, but relative. Time dilates, stretches, and bends, depending on one's speed through space. A moving clock ticks slower than a resting one. An astronaut racing near light speed would return younger than her twin left behind on Earth. What Newton had imagined as universal, Einstein showed to be intimate, personal, inseparable from the path one takes through the cosmos. A decade later, Einstein's general theory of relativity went even further. Time was not an independent stage, but part of the fabric of space-time itself, woven together with space into a single entity. Massive objects, stars, planets, galaxies, do not merely sit in space. They warp the fabric of space-time, bending the flow of time around them. Near a black hole, seconds stretch into eternities. Time itself becomes distorted, slowed to the edge of stillness. It was a revelation so profound that it seemed almost poetic. Time is sculpted by gravity, curved by the very matter it contains. The universe was not a rigid machine, but a pliable fabric, dynamic and alive. Yet even as relativity redrew the cosmos, another riddle emerged from the microscopic world. Ludwig Boltzmann, the Austrian physicist, had long before wrestled with a paradox. Why does time move only forward? The laws of physics, Newton's mechanics, Maxwell's electromagnetism, Even Einstein's equations are symmetrical in time. They do not forbid a film reel of reality from running backwards. A shattered glass could reassemble, a puff of smoke could gather itself back into a candle flame, a star could collapse and then rise whole again. The mathematics does not object, and yet the world we see refuses to play in reverse. Disorder increases. Glasses shatter but never reform. Smoke disperses but never recover. This one-way flow, Boltzmann explained, is the result of entropy, the measure of disorder. The universe began in an astonishingly ordered state, and ever since, it has been unraveling into greater and greater chaos. The second law of thermodynamics decrees: entropy must increase, and so, the arrow of time is born. But here lies the paradox. If time is simply another dimension in the fabric of space-time, as Einstein described, then why should it prefer one direction over another? Space does not. One may move left or right, up or down, forward or back. But time seems to grant no such freedom. It flows always, in one direction, from past to future, from birth to death, from order to decay. This contradiction opened a wound in physics. On one side, the equations of relativity and quantum mechanics suggested a universe where time was simply a coordinate, reversible and symmetric. On the other, entropy declared that time is irreversible, a relentless arrow. Two visions of time, both true, both irreconcilable. In this tension, the modern story of time begins. A story not of absolute certainty, but of questions that cut deeper than any machine or clock could measure. For beneath the ticking of hours lies a mystery. Is time a line, a circle, or an illusion altogether? The ancients saw a wheel. Newton saw a river. Einstein saw a fabric. Boltzmann saw an arrow. And somewhere between them all lies a secret, one that whispers of eternity, and of the possibility that time itself is far stranger and far less stable than we dare to believe. Time is a mystery not because it flows, but because it flows only one way. Every sunrise rises into tomorrow. Every heartbeat slips into memory. A glass shatters upon the floor, never to reassemble. Smoke unfurls into the air, never to return to the candle's flame. This direction, from past to future, feels so absolute that we rarely question it. Yet, when physicists look at the mathematics beneath reality, they find a disturbing truth. The laws of physics do not care about direction. Whether Newton's equations of motion, Maxwell's laws of electromagnetism, or even the equations of Einstein's relativity, they are all reversible. If a film of the universe were played backwards, the mathematics would not complain. A star could collapse in reverse. A planet's orbit could unwind. The waves of light could retrace their steps through space. The universe, in theory, permits yesterday as much as it permits tomorrow. And yet, reality refuses to obey. The arrow of time is undeniable. Broken eggs do not leap back into shells. Stars do not rewind into clouds of hydrogen. Life does not return to the cradle once it has dissolved into dust. There is only one way forward. The explanation came from a quiet Austrian physicist, Ludwig Boltzmann. In the late 19th century, Boltzmann wrestled with the strange connection between time and entropy, the measure of disorder. His insight was profound. While the laws of motion are symmetric, probability is not. There are infinitely more ways for matter to be disordered than ordered. A shattered glass has countless possible configurations. An intact glass, only one. Therefore, the universe, left to itself, will always tumble toward disorder. This became the second law of thermodynamics. Entropy never decreases. From it, the arrow of time seemed to emerge. The future is defined not by what is possible, but by what is overwhelmingly probable. But here lies the shock. If entropy is the engine that drives time forward, why did the universe begin in such an extraordinarily low entropy state? The early cosmos, just after the Big Bang, was astonishingly smooth uniform, and ordered a canvas of incredible simplicity. By all accounts, it should have begun in chaos. Yet it began in order, and only then unraveled into complexity. This enigma gnawed at physicists. Why the universe started this way remains one of the great unsolved questions of cosmology. Was it a necessity, written into the laws of physics themselves? Or was it an accident, a singular stroke of improbable fortune that allowed history to unfold? This fundamental asymmetry troubled scientists because it revealed a fracture at the very heart of physics. On one side were the time-symmetric equations of mechanics, relativity, and quantum theory. On the other, the irreversible march of entropy. The universe seemed to live in two languages that could not be reconciled. The paradox grew darker when physicists turned their gaze toward black holes. In the 1970s, Stephen Hawking discovered that black holes are not eternal prisons but evaporate, slowly, over cosmic timescales. They release a faint glow, now called Hawking radiation, until they eventually vanish. But in doing so, something terrifying appeared. The apparent loss of information. If matter falls into a black hole, and the black hole later evaporates into featureless radiation, the information about what fell inside, its structure, its history, its very identity, is gone forever. Yet the laws of quantum mechanics insist that information cannot be destroyed. Every wave function evolves reversibly. Every process, in principle, could be retraced. But if Hawking's black holes erase information, then the arrow of time is no longer a mere byproduct of entropy. It is a lawbreaker, an assassin of order. This became the infamous black hole information paradox. Was the universe, at its edges, violating its own rules of time symmetry? Was time itself flowing differently in the presence of gravity so extreme that it tore at the fabric of reality? Physicists debated fiercely. Some argued that information must somehow survive, encoded upon the event horizon in a subtle hologram of quantum bits. Others believed information might be scrambled, never lost, but transformed beyond recognition. Hawking himself changed positions over the decades, reflecting the unsettled nature of the question. What disturbed scientists most was not the specific fate of information, but what it implied. That at the most fundamental level, the arrow of time might not be universal. In the heart of a black hole, the rules could fracture. The smooth flow of cause into effect, past into future, could dissolve. The paradox deepens when considered against relativity. Near the edge of a black hole, time slows dramatically, stretched by gravity's grip. To a distant observer, matter falling in seems to freeze, suspended forever at the horizon. From another perspective, it plunges through. Two narratives of time, equally valid, yet utterly incompatible. Which one is true? The discomfort is not academic. If the arrow of time can bend, break, or reverse under such conditions, then time itself may not be the fundamental backdrop we imagine. It may be fragile, emergent, or conditional, not a stage upon which reality plays, but a property born from deeper laws, yet unseen. And so, the scientific shock persists. The arrow of time, so obvious in daily life, is in truth one of the most inexplicable features of the cosmos. It begins with a mystery. Why the infant universe was ordered at all. It grows with a contradiction. Equations that allow reversibility, and a world that denies it. And it darkens with black holes, where information itself seems to fall victim to time's irreversible hunger. Here, physics confronts something profound. Not only does time move forward, it may move differently at the edges of reality, or collapse into silence altogether. What began as the comfort of a ticking clock has become the most unsettling of questions. If time's arrow is not universal, then what is time? To study time is to study what cannot be touched. It is not a particle to be captured, nor a force to be bottled. It leaves no fingerprint but change, no shadow but memory. And yet, humanity has built instruments to chase its faint traces. Devices that look not for time itself, but for the signatures of its unfolding across the universe. The first true window into cosmic time came not from philosophy, but from the sky. In 1965, two engineers at Bell Laboratories, Arno Penzias and Robert Wilson, attempted to refine a radio antenna for satellite communications. Instead, they stumbled upon a faint, persistent hiss, a signal that seemed to come from every direction in space. What they had uncovered was nothing less than the oldest light in the cosmos, the cosmic microwave background, a fossil afterglow from 380,000 years after the Big Bang. When the universe first cooled enough for atoms to form and light to travel freely, this relic radiation became a clock, a snapshot of the universe's earliest ordered state. Satellites, such as COBE, WMAP, and Planck, would later map this faint glow with extraordinary precision, revealing its minute fluctuations. These patterns, ripples in ancient light, became evidence that the infant universe was not perfectly smooth, but slightly uneven, seeded with the structures that would grow into galaxies and stars. But beneath this triumph lay a deeper puzzle: the uniformity of the background itself. The light is almost the same temperature across the sky, so perfectly even that it suggests all regions of the universe were once in contact. Yet according to the speed of light and the universe's expansion, many of these regions could never have communicated. How, then, did they synchronize? Why is the early universe so smooth, so low in entropy, when randomness should have prevailed? This is the horizon problem, and with it, the arrow of time deepens into paradox. Instruments had revealed a cosmos whose beginning was improbably ordered, a stage upon which time's direction was set, and still, no one could explain why. While cosmology peered outward into the vast, quantum physics peered inward into the very small. Here, the laws of time grew stranger still. In the quantum world, particles do not move along fixed paths, but exist in superpositions, possibilities overlapping until observed. The equations governing them, Schrödinger's equation, are perfectly reversible. To the mathematics of the quantum realm, there is no difference between forward and backward. Richard Feynman once reimagined the electron itself as a particle that, in some interpretations, might be thought of as moving backward in time. Antiparticles, the mirror opposites of matter, can be described mathematically as particles retracing history in reverse. In experiments, photons interfere with themselves as though they have taken every possible path, both past and future, simultaneously. To quantum mechanics, time is not a river but a mirror, with no preferred reflection. And yet, when observed, the probabilities collapse. Outcomes become fixed. The quantum haze resolves into one history, and always forward. Some physicists wondered, could entropy itself be tied to observation? Could the arrow of time emerge only when possibilities are reduced to actualities? When consciousness or measurement imposes order on the quantum? Others sought evidence in the subtle asymmetries of particle physics. In 1964, James Cronin and Val Fitch discovered that certain subatomic particles, kaons, violate CP symmetry, meaning their behavior slightly favors matter over antimatter and forward over backward in time. This tiny fracture in symmetry, detected in accelerators and confirmed in later experiments, suggests that time, at its most fundamental level, is not perfectly reversible after all. The universe, it seems, is biased, however slightly, toward a particular direction. Instruments like the Large Hadron Collider continue to search for such cracks in the symmetry of nature, hoping that in these small imbalances lies the secret of why the arrow of time exists, why matter dominates over antimatter, and why the universe began as it did. Yet, as scientists probed deeper, anomalies emerged that resist explanation. The Planck satellite detected patterns in the cosmic microwave background that hint at alignments across the largest scales of the universe. Strange symmetries that suggest the cosmos may have deeper structures than we imagined. Some physicists whisper of a pre-Big Bang era, encoded in these faint patterns, where time itself may have behaved differently. Meanwhile, in the silence of underground detectors, others search for dark matter, the unseen mass-shaping galaxies. If found, it may alter our picture of entropy, for dark matter may carry its own hidden order, its own rules of time. And above it all, telescopes like Hubble and the James Webb Space Telescope gaze into the most ancient light, seeking the first galaxies, the earliest structures that emerged from the ordered cosmos. Their data stretches the arrow of time backward, closer to the dawn, to test whether the rules of change were always as they are now, or whether time itself behaved differently in the young universe. At the same time, the science of gravity waves has opened a new frontier. In 2015, LIGO recorded the collision of black holes, ripples in space-time itself, sweeping across Earth. These signals carry information from the most violent events in cosmic history, events that test relativity under conditions of extreme curvature. If time can bend, falter, or collapse, such cataclysms may reveal its weakness. The waveforms recorded are not merely vibrations of space. They are records of time's own fabric, trembling. Through these instruments, science has learned that time is not uniform. It slows in gravity's grip, dilates near light speed, bends around stars, and vanishes at horizons. The era we perceive may be only one layer, one emergent property of a deeper structure. Perhaps time is not fundamental at all, but a shadow of entropy, or a construct of quantum entanglement, or a byproduct of conditions at the birth of the universe. And so, the deeper we investigate, the less certain time becomes. Our tools reveal its fractures, its asymmetries, its strange reluctance to obey its own laws. It is everywhere, shaping galaxies and lives, and yet nowhere. Untouchable, unseen, intangible. The instruments of eternity have shown us much, but left us haunted by more. If the cosmos began in improbable order, if quantum laws permit reversibility, if black holes threaten to erase information, then time is not the absolute guide we thought it was. It is fragile, it is conditional, and perhaps it is destined, someday, to collapse. What began as a search for clarity has led instead to deeper fog. The further we look, the more the arrow bends, the more eternity itself seems to tremble. Here, in the faint hiss of ancient light, in the flicker of particles, in the trembling of space-time, lies a warning. The universe does not obey the story we tell of time. It hides another script, one that may reveal itself only when time itself comes undone. The further science peers into the cosmos, the more fragile the arrow of time appears. What once seemed eternal, flowing steadily from past into future, now wavers at its edges. There are places in the universe where time itself seems to hesitate, where the rules falter, where the story of cause and effect unravels. At the scale of the entire cosmos, the first fracture emerges in the fate of expansion. For decades, physicists believed the universe might one day halt its outward rush. Gravity, the great sculptor of motion, could eventually slow expansion until galaxies reversed their course, collapsing back toward one another. This vision became known as the Big Crunch. In such a scenario, the arrow of time itself could bend back upon itself. Entropy, having increased for billions of years, might reach its peak and then begin to unwind as the universe collapsed into order once more. A cosmic film played in reverse, stars unburning, galaxies unweaving, life unliving. But evidence revealed something stranger. In 1998, observations of distant supernova showed that the universe is not slowing, but accelerating. Some hidden energy, now called dark energy, is pushing galaxies apart faster and faster. The cosmos may not collapse at all, but continue expanding into an endless void. Its galaxies drifting beyond visibility, its stars burning out into darkness. This deepens the paradox. Entropy rises forever, yet time's arrow never resets. Eternity becomes not a cycle, but a slow, infinite death. Still, the possibility of reversal haunts theory. If expansion can accelerate, could it not also decelerate at some unfathomable future? Might dark energy change its nature, turning from repulsive to attractive, dragging the universe back into collapse? In such a fate, time might not merely stop but collapse inward, crushing history into a singular point. Einstein's relativity itself contains the seeds of such contradictions. Within its mathematics exist solutions known as closed, time-like curves, paths through spacetime that loop back upon themselves. A traveler following such a curve could return to her own past, tracing time not as a line, but a circle. In theory, rotating black holes or wormholes could harbor such loops, bending time into a paradox. If such structures exist, then the arrow of time is not universal but local. One direction here, another direction there. The river splits, eddies, and circles back upon itself. These possibilities are not merely abstract. They threaten the foundation of causality itself. If time can fold into loops, then cause and effect dissolve. A consequence could precede its cause. A universe that collapses back upon itself could erase its own history or repeat it endlessly, with no beginning and no end. This is the terror of time's instability, that the most basic assumption of existence, that the past is fixed, and the future unknown, may not hold in the deepest fabric of reality. Nowhere is this instability more extreme than at the edge of black holes. At the event horizon, time stretches toward infinity. To a distant observer, matter falling inward never crosses the threshold. It slows, reddens, and fades into stillness. But to the matter itself, time proceeds as normal, rushing inward past the horizon. Two realities coexist. One where time halts, another where it continues. Which is true? Both. Neither. Inside, the singularity awaits. A point where gravity becomes infinite, space-time collapses, and time ceases to have meaning. Here, relativity itself breaks down. The arrow of time cannot be defined, because time itself no longer exists. Stephen Hawking once warned that singularities represent the edge of knowledge, the place where physics itself collapses. In these regions, the laws that govern everything else in the universe dissolve. What remains is speculation, whispers of quantum gravity, strings vibrating across unseen dimensions, or space and time as emergent illusions from deeper, timeless structures. And yet, the singularity may not be unique to black holes. Some cosmologists argue that the universe itself began in one. If the Big Bang was a singularity, then the arrow of time began not in continuity, but in rupture. In that instant, time did not simply move forward. It began, emerging from a place where no before existed. If time could begin, could it not also end? Could the arrow itself collapse, erasing both memory and possibility, in one final silence? Other theories push further. Roger Penrose's conformal cyclic cosmology imagines that the heat death of the universe, when all matter decays into radiation, is indistinguishable from the Big Bang itself. The end of one universe becomes the beginning of another. Time, in this view, is not linear but recursive, cycling through eternities. The arrow collapses only to rise again. Each eon gives birth to the next, and what we call the beginning is merely one moment in an endless chain. In this, time is no longer a straight path, nor even a single loop, but an infinite chain of collapses and rebirths. Each collapse is not the end, but the folding of one story into the beginning of another. And yet, perhaps the most chilling possibility lies not in cycles, but in silence. If dark energy continues its acceleration unchecked, galaxies will drift beyond one another's reach. Stars will exhaust their fuel, black holes will evaporate, and the cosmos will become a thin mist of radiation, expanding forever into nothing. In such a future, the arrow of time does not reverse, but it loses all meaning. With no processes left to unfold, no entropy to increase, time itself would become indistinguishable from stasis. Eternity would collapse not in fire, but in silence. This is the escalation. The realization that time is not guaranteed to obey its own rules. It may collapse, loop, reverse, or dissolve. It may end not with a bang, but with a stillness so complete that the difference between past and future ceases to exist. The instruments of eternity have revealed only fragments of this truth, glimpses of time's fragility at cosmic extremes. The rest is speculation, mathematics pointing to paths where human intuition falters. But the warning is clear. The arrow of time is not the absolute compass it appears to be. It is provisional, conditional, perhaps even an illusion. And so the mystery deepens. If time can break its own rules, then what rules remain? If the arrow can collapse, what remains of eternity? Time, the one dimension that seems to carry us relentlessly forward. And yet, the deeper science peers into its nature, the more uncertain its foundations appear. For every equation that permits reversibility, there is an arrow pointing forward. For every theory that explains its flow, there is a paradox that defies it. Out of this fracture, physicists and philosophers have woven speculations, visions of eternity that challenge the very meaning of past, present, and future. One of the oldest questions resurfaces in modern physics. What is time itself? Is it a fundamental feature of reality, or an emergent property born from something deeper? Here, theories diverge, each a different attempt to reconcile the irreconcilable. Eternalism versus presentism. In philosophy, two visions dominate. Presentism declares that only the present is real. The past is gone, the future not yet, and the now alone exists. This view resonates with human intuition. Every heartbeat, every moment, is fleeting, dissolving into memory. But physics often points instead toward eternalism, the idea that past, present, and future all coexist equally, as parts of a four-dimensional block universe. In Einstein's relativity, time is simply another coordinate, like length or height. The universe does not unfold. It simply is, a vast, frozen sculpture where every event, from the birth of stars to the death of galaxies, is already inscribed. The flow of time, in this view, is not a property of the cosmos, but of consciousness. A trick of perception as we move along our world line. If eternalism is true, then time cannot collapse, for it never truly flows. Eternity is not a stretch of infinite duration, but a single, complete whole. And yet, if presentism holds, then the collapse of time would mean the collapse of reality itself, the annihilation of the only now that ever exists. Quantum timelessness. Deeper still lies the realm of quantum mechanics. Here, the arrow of time dissolves into something stranger. The Wheeler-DeWitt equation, a central equation in attempts to unify quantum mechanics with general relativity, describes the universe as a wave function outside of time. In this equation, there is no t, no variable of time at all. The cosmos exists as a timeless quantum state. Change, and thus time itself, may be an illusion that emerges only when parts of the universe are compared to others. Physicist Carlo Rovelli has championed this idea, suggesting that time is not fundamental, but relational. Clocks tick not because of some universal river, but because systems change relative to one another. A pendulum swings compared to the Earth's rotation. A heart beats compared to the diffusion of oxygen. Without these comparisons, time evaporates. In this sense, entropy, the spreading of disorder, may be the only true arrow, giving rise to the appearance of past and future. If this is so, then time could indeed collapse back upon itself. If entropy were ever to decrease, against the second law of thermodynamics, then the arrow would reverse. What we call the future would no longer be distinguished from the past. History could fold, moments could repeat, eternity could loop endlessly without progression. Vacuum decay and the reset of time. Another speculation lies in the precarious foundation of reality itself. The vacuum of space, though seemingly empty, may not be the lowest possible state of energy. Some physicists fear that our universe exists in a false vacuum, a metastable state that could, at any moment, collapse to a more stable one. If such a decay occurred, it would release catastrophic energy, rewriting the laws of physics, obliterating particles, and perhaps resetting time itself. In such a scenario, eternity is fragile. All that we call history, memory, and order would vanish in an instant, replaced by a universe with new rules, where time may not flow as it does now. To contemplate vacuum decay is to contemplate the fragility, not just of matter, but of time itself. The possibility that eternity could be erased and replaced without warning. The multiverse and divergent arrows. Speculation expands further when one considers the multiverse. If our universe is only one of countless others, each birthed by inflation or quantum fluctuations, then time itself may not be universal. In some universes, the arrow may flow as it does here, from low entropy to high. In others, the arrow may reverse, with entropy decreasing, universes running backward, from our perspective. There could even be realms where time is not one-dimensional at all, but branched, cyclic, or altogether absent. The implications are unsettling. If the multiverse is real, then eternity is fractured. What we call time is not universal, but provincial, a local property of this cosmos, this arrow. Elsewhere, eternity might be an endless loop, a frozen block, or a collapsing spiral. Cosmic inflation and the birth of time. Another theory points toward the beginning. Cosmic inflation, the rapid expansion of the universe in its first fraction of a second, may explain why the cosmos began in such low entropy. Inflation stretched quantum fluctuations into vast uniformity, creating the ordered beginning from which the arrow could emerge. If so, then time's direction is not a mystery, but a consequence of inflation's smoothing power. Yet even here, the paradox persists. If inflation is eternal, creating bubble universes without end, then time is infinite and cyclical. Each bubble begins with low entropy, each arrow reset. In such a multiversal eternity, collapse and rebirth are not exceptions but the rule. The holographic principle in time's encoding. Theoretical physics offers one more extraordinary possibility: that time itself is encoded, not in the fabric of space, but on its boundary. The holographic principle suggests that all information within a volume of space can be described on its surface, like a two-dimensional hologram projecting a three-dimensional image. If true, then perhaps the arrow of time is not a feature of the universe itself, but of this holographic encoding. Time's flow could be an emergent property of how information is stored on cosmic horizons, such as black holes, or even the edge of the observable universe. If so, then time might collapse not within the universe, but at its boundaries. At horizons where information is lost, scrambled, or distorted, the arrow could fracture. Eternity itself could be a projection, fragile, contingent on a deeper law we have not yet glimpsed. The paradox of eternity lies in this convergence of speculation. Is time fundamental, or emergent? A river, a wheel, or an illusion? Does eternity stretch forever forward, or collapse into cycles, loops, or silence? Theories diverge, yet all point to the same unsettling truth. Time is not what it appears. It is fragile, conditional, perhaps even doomed to collapse. If it is eternal, it is not in the way humans imagine. Not a steady line stretching into infinity, but something stranger, darker, and far more mysterious. Perhaps eternity is not the endless march of time, but its absence. Perhaps the true paradox is that eternity requires time's collapse. The mysteries of time are written not only in philosophy and theory, but in the light of stars, the trembling of space-time, and the smallest fragments of matter. To chase these mysteries, humanity has built tools of unprecedented power. Instruments that reach across billions of light years, that listen to the faintest echoes of the past, and that probe the quantum depths where time itself may be hiding its secrets. These instruments are not merely machines. They are lenses through which eternity is tested, stretched, and questioned. Each one extends human perception into realms where the arrow of time bends, where symmetry fractures, where history itself may dissolve. The telescopes of origins. Above the atmosphere, the Hubble Space Telescope has, for decades, gazed deeper into the universe than any eye before it. In its mirrors, astronomers see not just distance, but time. Every photon captured is a messenger from the past, sometimes billions of years old. In Hubble's deepest fields, galaxies appear as they were near the dawn of cosmic history, when the universe was young and entropy still low. These images are not just pictures. They are fragments of the arrow of time, frozen into light. But Hubble was only the beginning. Now, the James Webb Space Telescope carries humanity's vision further still. Into the first stars, the first galaxies, and perhaps into the faint shadows of inflation itself. Webb's infrared gaze pierces through dust and darkness to see light stretched by cosmic expansion, light that carries the signature of time's first unfolding. By measuring the earliest structures of the cosmos, scientists hope to understand why time began with order, and whether that order was inevitable or improbable. Each observation tests the nature of time's beginning. Each galaxy observed near the dawn is not only a piece of history, but a test of the laws that gave time its direction. If Webb uncovers anomalies, patterns inconsistent with inflation or entropy, it may hint that time itself emerged in ways we do not yet understand. The trembling of space-time. While telescopes reveal the past in light, another instrument listens for the past in soundless waves. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO recorded the first direct detection of gravitational waves, ripples in space-time itself, born from the collision of black holes over 1 billion years ago. These ripples are not merely disturbances of space, they are tremors in time. When a wave passes through Earth, time itself stretches and compresses by the tiniest fractions, measurable only by lasers fired across kilometers of vacuum. The waves carry information about events so extreme that they bend the very fabric of causality. With every detection, LIGO and its counterparts, Virgo in Europe, Kagra in Japan, and future observatories in space such as LIS, open a new window into the structure of time. In the cataclysmic mergers of black holes and neutron stars, space-time is twisted to its limits. Here, physicists search for deviations, subtle hints that the arrow of time may fracture under such immense strain. If black holes truly erase information, as Hawking once feared. Gravitational waves may carry the faint fingerprints of that erasure. If time collapses at horizons, then the ripples born from those horizons may reveal it. Every detection is not only an observation of violence, but a test of eternity itself. The particle accelerators of symmetry, beneath the Earth, in vast underground tunnels. Another set of instruments probes time at the smallest scales. The Large Hadron Collider, LHC, a 27-kilometer ring beneath Geneva, smashes protons together at near-light speeds, recreating conditions that existed only trillionths of a second after the Big Bang. Here, physicists study the delicate symmetries of particles. In 1964, CP violation was first observed, the subtle preference of certain decays for matter over antimatter. This violation is also a violation of time symmetry. It hints that, at the deepest level, the laws of physics are not perfectly reversible. The LHC and other accelerators continue to test this fracture, measuring whether time's arrow is inscribed into the fabric of quantum interactions themselves. If greater asymmetries are found, they may explain why the universe contains matter at all, why the Big Bang did not create equal amounts of matter and antimatter that would annihilate into nothing. In this, the very existence of galaxies, stars, and life depends on the direction of time. Future colliders, even larger than the LHC, are being designed to push deeper, probing energies where new symmetries may emerge, or collapse. At such scales, time may reveal itself not as fundamental, but as an emergent property of quantum fields. Quantum experiments of reversibility. In laboratories across the world, physicists also test time, not with colliders or telescopes, but with controlled quantum experiments. Quantum computers simulate systems evolving, both forward and backward, testing whether time symmetry holds in practice. Some experiments have already produced eerie results, in which systems appear to partially reverse their evolution, as though the arrow of time could briefly bend. Other teams probe entanglement, the strange correlation between particles separated by distance. Entanglement suggests that time and space themselves may be emergent, that the flow of time could arise from the growth of entanglement across the universe. If so, time is not a river, but a network of relationships, fragile, contingent, and collapsible. In cryogenic labs, physicists cool atoms to near absolute zero, halting motion to glimpse time almost frozen. Here, researchers ask whether entropy can truly reach a standstill, whether the arrow can ever stop. The answer remains elusive, but each attempt narrows the boundary between motion and silence, between time and eternity, dark energy and the fate of time. At the largest scales, instruments also chase the force that accelerates the universe's expansion. Through projects such as the Dark Energy Survey, the Euclid Telescope, and the Vera Rubin Observatory, scientists map galaxies and measure how space stretches. Their aim is to understand dark energy, the mysterious pressure that may decide the ultimate fate of time. If dark energy is constant, expansion will continue forever, stretching galaxies into isolation, driving the universe toward heat death. If it evolves, it may reverse, pulling everything back into collapse, perhaps collapsing time itself. The data is still incomplete, but each survey brings us closer to answering the most profound question of all. Will time end in silence, or in fire? The search for quantum gravity. Perhaps the deepest effort of all lies in the attempt to unite relativity and quantum mechanics, to discover a theory of quantum gravity. In string theory, loop quantum gravity, and holographic dualities, time itself becomes secondary, an emergent property of deeper structures. These theories suggest that at the Planck scale, unimaginably small, time may not exist at all. Instead, what we call time may emerge only at larger scales, like temperature emerges from countless particles in motion. Testing such ideas directly is nearly impossible. Yet through black hole physics, cosmological surveys, and gravitational waves, glimpses may emerge. If time is emergent, then its collapse is not an end, but a transition. A return to a more fundamental timeless state beneath. Time, then, is not beyond science's reach. It is being tested, stretched, and measured by machines of almost unimaginable scale and precision. The telescopes reveal its birth. The detectors hear its tremors. The colliders fracture its symmetries. The quantum labs probe its reversibility. and the cosmological surveys map its destiny. Each discovery narrows the possibilities, yet each also deepens the mystery. For every confirmation that entropy drives the arrow forward, there is a black hole that threatens to erase it. For every symmetry confirmed, there is a violation that breaks it. For every experiment of reversibility, there is a collapse into chaos. The paradox grows sharper. If time can be tested, then it can fail. If it can collapse, then eternity itself is fragile. And so, the search continues. Humanity reaching across the void with instruments of light, sound, and matter, straining to hear the faintest whisper of eternity. For in those whispers may lie the answer to the most haunting of questions. Is time real, or is it only the shadow of something deeper? There is a silence beneath the ticking of clocks. A silence that no machine can measure, no equation can fully explain. It is the silence of eternity. The question of what time means when stripped of its arrows, its beginnings, and its ends. For all the instruments humanity has built, for all the mathematics that have mapped stars and particles, there remains a shadow across the heart of physics. The arrow of time is visible everywhere, yet its cause remains hidden. The paradox is that eternity cannot be understood only by science. It demands also reflection, philosophical, existential, human. The fragility of memory. Time is felt most intimately in memory. The past seems fixed because it lives in recollection, the future uncertain because it lives only in imagination. If time were to elapse back upon itself, what would happen to memory? Would history be erased, as if it had never been? Or would the universe repeat endlessly, each cycle replaying the same memories, the same choices, the same tragedies and joys? Some philosophers have imagined an eternal return, the idea that all events recur infinitely. In such a cosmos, memory becomes a cruel illusion, for the present is not unique, but one of countless repetitions. Others have imagined the opposite, that collapse would erase memory altogether, leaving only a stillness where neither past nor future survives. In this, eternity is not repetition, but silence. For the human heart, both visions are terrifying. One condemns us to an endless cycle we cannot escape. The other extinguishes us into nothing. Yet both remind us that time is not merely physics. It is the fabric of identity, of meaning, of being itself. The human assumption. Civilizations have always lived with one assumption, that time flows forward. Every law, every story, every dream rests upon it. Birth leads to growth, growth to decline, decline to death. Yet the universe suggests that this may not be fundamental, but conditional. If time can break, collapse, or vanish, then meaning itself becomes fragile. For what is human life without time? Without the sequence of moments, there is no narrative, no progress, no hope. Eternity, far from being comfort, becomes the greatest abyss. To confront it is to confront the possibility that all meaning is provisional, suspended on the fragile arrow of entropy, and yet this confrontation is also liberation. For if time is not absolute, then neither is destiny. If the future is not fixed, then the present carries infinite weight. In this way, the fragility of time gives strength to the moment, to the now. The philosophical shapes of eternity. Philosophy has long wrestled with eternity. In some traditions, eternity is timelessness, the absence of before and after, a state beyond change. In others, eternity is infinite duration, a time that never ends. But physics suggests a third possibility, that eternity is paradox, a structure where time collapses back upon itself, where beginnings and endings merge. If the block universe of relativity is true, then eternity is the whole of space-time, already complete, never growing or shrinking. If cyclic cosmologies are true, then eternity is endless return, the wheel turning forever. If entropy reaches its maximum, eternity may be silence. No change, no difference, no arrow at all. Which of these visions is real? Perhaps all of them, in different scales, in different contexts. Perhaps eternity is not singular, but manifold. A paradox that shifts depending on where one stands in the cosmos. The cosmic river and the eternal wheel. Human imagination often returns to metaphor. Time as a river, flowing from source to sea. Time as a wheel, turning endlessly. Both are ancient, Both survive in modern science. Relativity gives us the river, flowing differently depending on its banks, slowed by gravity, accelerated by motion. Thermodynamics gives us the wheel, cycles of order and disorder, universes born and collapsing. But both metaphors fail at the singularities, at the beginning, at the black holes, at the hypothetical collapse. There, the river does not flow, the wheel does not turn. Time itself ceases to exist. Eternity is not flow, but rupture, not motion, but absence. This is the hardest vision for the human mind. That eternity is not infinite time, but the absence of time. That what lies beyond the arrow is not endless extension, but something altogether alien to experience. Eternity and consciousness. If time collapses, what happens to consciousness? The human mind is built on sequence. One thought after another. One memory following the last. Without time, there can be no narrative self, no continuity of awareness. Some argue that consciousness itself may be an arrow of time, born from entropy's growth, dissolving if entropy were ever to reverse. Others imagine that awareness could survive in a timeless state, not as narrative, but as presence, a pure now, without past or future. This resembles mystical traditions across cultures, where eternity is described not as endless time, but as an eternal present. Perhaps science and mysticism touch here, at the edge of language, where time itself collapses. The weight of unanswered questions. Even as telescopes peer deeper, even as colliders probe further, the mystery of time remains. Why did the universe begin in low entropy? Why do the laws allow reversibility, while reality refuses it? Why does information seem threatened at black hole horizons? Why does dark energy push eternity outward into silence? These unanswered questions reveal something profound. The more humanity learns, the more fragile time appears. Each discovery deepens the paradox. Each test reveals fractures. Eternity is not certainty, but uncertainty, not stability, but tension. And yet, this very uncertainty is the heart of wonder. For if time were simple, eternity would be dull. It is the paradox, the collapse, the fragility, the mystery, that gives the universe its haunting beauty. Perhaps the true meaning of eternity is not in clocks, nor in equations, but in awareness of the mystery itself. Eternity is the recognition that time may collapse, that the arrow may falter, that the universe may dissolve. Eternity is not a promise of infinite life, but a reminder of fragility, of impermanence, of wonder. For when humanity stares into the cosmos, into the galaxies drifting outward, into the light of the first stars, into the silence of black holes, it is not only seeking knowledge of time, it is seeking meaning in the face of eternity. And perhaps that meaning is this. Eternity is not an endless future, but the endless presence of mystery, a silence deeper than time, a question that can never be answered, because the answer itself lies beyond time.